Hello everyone, welcome to a new video on electromagnetic fields. So in today's video we are going to discuss an important topic which is the curl of a vector. We already discussed about what is meant by gradient, what is divergence, and now we are going to discuss about curl. We know that gradient is taken over a scalar and divergence is measured for a vector. Similarly, curl is also measured for a vector. So in this video we are going to discuss deep about curl with some hands-on explanations and some basic testings with real life applications. So in today's video we are going to visualize a swirl, which is the other name for curl, and we are going to define what is meant by curl, and let's get a hands-on exploration on how to visualize the vector field directions using interactive activity, and then let's analyze the rotating vector fields through some prototypes, and then we'll have a quizzing session. First, let's visualize a curl. Curl means swirl. First, let us imagine the swirling of a smoke, the swirling of water, the swirling of oceanic waves. For example, if you have a water in a bowl and if you swirl it with your hand, you can observe the motion, the concentric motion of the water waves, which is nothing but a curl. These everyday observations are a perfect starting point for understanding curl. The curl quantifies the tendency of a vector field to rotate. So, any vector field of an object in which direction it swirls, that can be given using the concept curl. Now let's get into an hands-on exploration. How to feel the motion of a curl, what direction it is. Okay, let's take a bowl, put some balls in it, close the lid, and now like what you observe in the image, hold it and now start moving it in the clockwise direction. When you hold the bowl and move in clockwise direction, you can observe your thumb, which points upwards, will indicate the direction of the curl vector. So if you want to observe the curl vector direction, then it will be indicated by the thumb. So this represents that the field is rotating out of the page, which means that it rotates outwards. So if you rotate the bowl in anti-clockwise directions, which is in counterclockwise motion, now you can feel that the ball rotates in left-handed manner, which means that your thumb of the left hand will point downwards, illustrating that the curl vector is directed into the page. So the direction of rotation or the motion of the curl will be in opposite direction, which shows that it is rotating inwards. So using this hands-on explanation, hands-on experience, you can easily teach what is a curl or how it rotates, how it swirls to the students. So now let's get into a prototyping model. For here we have shown a field, a vector field. Now we are going to analyze at what point the curl will be maximum or will be zero or it is less. So let's visualize where the curl is strongest in a rotating field. Okay. For example, if you take a bowl of water and if you swirl it, you can easily find the swirling of the water, right? Now we have to analyze where the curl, the swirling will be at its maximum. Okay. So when you observe deep into that swirling, you can find that at the very center of the rotating field, at the swirling of water, the rotation is localized and the linear velocity of particles is minimal. So the curl is the measure or the tendency to rotate. So here when you observe that swirling, the curl will be highest at the from the center point. So if the curl is actually maximum at this, which means that at the center the curl will be maximum. So if the curl is actually maximum at the center of rotation, even though the particles at the very center might not be moving, the surrounding particles are creating a stronger rotational effect around that point. So the curl will be maximum at the center point. Though it is maximum at the center point, the counterparts, the swirling effect will make the rotational effect around the point. But as you move away from the center point, the curl value might decreases, because we can observe that while swirling the water, we can easily observe the circles which are far away from the center will have a lesser effect, lesser swirling effect, whereas the point at the center will give a 100% swirling, right? So depending on the specific field, for a rigid body the curl is constant, and for a liquid like particle the swirl value may vary. So now these are the real world scenarios where you can observe a curl. So these are atmospheric vortices and oceanic currents, like what I've given the example of swelling of water in a bowl. So that is a simple example. In a broader view, you can see these also a example for curl. Now let's see where this curl is applied. Mathematically, this curl can be given as del cross the field. For example, let us assume the vector field as A. Mathematically, let us assume that vector field, any vector field, it can be electric potential or any vector. Let the field be, vector field be A, then mathematically a curl can be denoted as del cross A, where del is the nebula, dou by dou x into ax cap plus dou by dou x into ay cap plus dou by dou x and dou z into az cap. So this curl will give the magnitude as well as the direction of the swirling. Okay, so where this curl is actually applied? First, it is applied in electromagnetism. Yes, the Faraday's law of electromagnetic induction and Ampere's law, these utilizes curls to describe the relationship between changing magnetic field and electric fields and vice versa. How the magnetic field changes with respect to the electric field and how the electric field changes with respect to the magnetic field. These can be clearly explained because these fields, as we know, the magnetic field, it swirls, and so as the electric field. So this swirling effect or the twisting effect of these fields can be easily understood and visualized only through the concept of curl. And curl is the foundational understanding for fluid dynamics. Yes, the fluid flow, turbulence, the generation of vortices in liquids and gases, everything can be understood only through this curl. So this is a vital concept in aerospace engineering and also in heavily used in meteorology. And in robotics and navigations also, this curl understanding helps in path planning for autonomous vehicles, especially in avoiding rotational obstacles or navigating through complex fluid environments, etc. So now let's get a quick knowledge check. Which of the following statements is true about curl of a vector? It measures the divergence of the field. It quantifies the rotational tendency of the field. It is always a scalar quantity. It is only defined for 2D vector fields. Which one is correct? Like what the answer said, the correct answer is B. It quantifies the rotational tendency of the field. How much a field rotates, how much the field twists, that can be quantified only through the concept of curl. So through this video, we have a deeper understanding with real-time examples of how a curl provides a powerful mathematical tool to describe rotation in vector fields, and also it has given a wide-ranging applications understanding from weather patterns to fluid mechanics also. And also through this curl, we can understand the diverse vector fields around us. So through this video, we can get a clear knowledge about what is meant by curl and how it creates an impact in each and every uh, field like electromagnetism, fluid mechanics, and in aerospace engineering. Hope this video is very useful to you, and in the upcoming videos we'll deal with a new concept. Thank you. Thanks for listening.